All right, how we doing, everybody? All good? We just had an exam today. Laplace transforms. Fun, easy, hard, not that bad. It was an okay exam. Dr. Stewart is going to get all those exams hopefully graded soon. He was here today. He just didn't want to come to 360. He wanted to go to 480, which didn't have an exam. So that's why he was saying I'll proctor for the exam today. So less walking for him. He's on his little scooter. You guys saw him Monday, right? Yeah, so he was okay though, right? Yeah, just walking around. So yeah, he didn't want to do too much walking, so that's why I was proctoring. So he'll get our exams. Hopefully, I think he'll be in normally for Monday's lecture, so he should be here this Monday. So, anyways, and the assignment that's going okay. You guys figured out. It's just a system. You just kick the box, impulse response, step response. Not that bad, right? And then you guys, he hasn't talked to you at all about the Z domain, correct? Z transforms? No? All right, I'll give you guys your hint. So, congratulations, everyone. You guys finally made it. We're finally in the new domain. So you guys have been dealing with signals, S, our S domain, right? Where we're in analog. So all our signals are going to be like, I don't know, wiggly or something like this, right? A, e to the st, correct? Where if in this condition, s has got to be less than 0, so it's a negative number, right? And we go forward into time, right? T. Does that make sense for everyone? This is all basics, right? So now we're going to enter a domain where, actually, if I were to explain this, I'll just draw its little Laplace transform, L of S, correct? And then this pole is like, let's just say, it's right here, S, right? And then if I wanted to draw its region of convergence, right, it converges like that, right? And it's stable because we include this imaginary axis right here, right? Imagine, right? Imaginary. We include that, right? And it's causal because we're going right-sided, right? It's a right-sided right hand or right. It's a right-sided equation, right-hand equation, all right? Everyone got that on their exam, right? They saw, consider a stable system, but was it a causal system? Or wait, this is stable, this is causal, right? Causal because we go all the way. It's a right-handed function, but let's just say if it was like, I don't know, if it were this condition, like you can make a stable system, but it might be non-causal if it did this, right? That's non-causal because it's right-handed, but a left-handed that's doing it like this. Yeah, so consider a stable, and he didn't even say it was causal. So I don't know. I don't know what you guys' answers were. So is that making sense? You got. I'm trying to explain it because this takes us to an introductory to like I'm trying to show you guys like right-sided planes, left-sided planes, and then this like kind of like I don't know, like a chocolate bar or something like that. But the reason what I'm trying to say is, suppose I wanted to go into the new domain, like a Z domain, right? So now we're starting to deal with digital signals, right? And that's the whole point of signal theory is, I think from here is where we start splitting to, okay, you got controls domain, so stuff starts becoming more control theory, so you go into analog. But if you stick with DSP, we're going to stay with Z's. So the way that I'm going to show you is that your S turns into a Z, but you can define the Z as a e to the j omega, where this is basically, well, omega is equal to 2 pi, I don't know, 2 pi n, question mark, or 2 pi n. Oh, there we go. Yeah. I'll just ignore that, 2 pi k. But anyways, 2 pi f. There we go. I'm forgetting my little stuff. But anyways, with the Z domain, it's not that bad. We're just sampling, resampling stuff. So if I wanted to show you something quick, because I don't want to go too crazy on this, I'll let Dr. Stubert handle that. Is that you guys are used to this, where Laplace, right? Yeah, let's just say if I wanted to say this is, if you included this axis right here, right? This is our stable, right? Stable axis, right? Right? So let's just say there's a way that we can wrap this like a donut and create a circle. So this is going into like some infinity frequency or something like that. And this right here is going to some negative frequency, going to negative. And we start sampling. There's no other good way to say it, but we can wrap this into a circle where if you know that if a pole is right here, let's just say our pole is right here, that's a stable pole, right? Right? And we know that this side, if we have any poles on this side, it's stable, correct? So if there's another pole here, it's a stable pole, right? Is that good? So if I wanted to like circle all this, if I try to like create some like domain that like circles this, we can translate it to the following. Our Z domain. Where you can do the following. Draw a circle. Yeah, there we go. Is that a good circle? Yeah, it's okay. Where this is 1, it's -1, and then this right here is our imaginary axis. Anyways, this right here, this line right here is our imaginary axis. All right, and then what's inside here, if I were to color it in this kind of color, like this right here is our stable poles, right? Is all this stuff in here. Okay? So if I were to redraw this pole right here, it's a stable pole, okay? Because our region of convergence, if I were to draw a region of convergence as this purple color, let's just ignore this pole for a second. If I were to do this region of convergence, right? Let me draw it like this, right? ROC, okay? If I were to do the same thing for this donut, if I were to do this is at, I don't know, 0.9. This right here is -0.9, right? Draw that circle donut and draw a region of convergence like this. And then you'll just see this super donut. So it's stable because we include the imaginary axis, right? And it's also causal. Okay, because we're going, it's a right-sided function. See, it's right-sided, we're going to the right, and our pole is in this like stable, like stability pole, right? It's in this circle, unit circle, right? Is that making sense? But anyways, and then someone's asking me, how do I even use this? Why would I even want to care or whatever? If I wanted to show you examples, so there's another domain I want to show you. So he won't teach you this until you get to 361, is this line right here. You can technically get like a Fourier transform from this line right here, okay? This line, if you wanted to draw that stable line. Same thing with this blue line right here. You can get a Fourier transform just by running around the circle where this right here is your frequency at 0, right? AKA DC. That's where our DC analysis is going to happen. And then this right here was, if you wanted to, F is like infinity or something like that at this point right here. But in terms of just our digital domain, there's no such thing as like high frequency or infinity frequency. It's just our highest frequency at that point, okay? Is that making sense with everybody? Anyways, so let's look at your homework or your assignment, and I think this is where I want to understand what we're going to try and do with your accreditation. So let's see, signal processing toolbox, same thing. You got your B's, you got your alphas, correct? And then it's saying, okay, you have negative z poles. Okay, yeah, z to the negative m and z to the negative n, right? Good. You can rewrite this as, what do you call it? Positive poles. So you have this, 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 this. And you can do the same thing like we did in assignment 5, computer assignment 5, with computer assignment 6. But there's an exception. You need to make sure that the poles are equal, okay? So that the top and bottom numerators are the same length. They're equal TF length, equal length. I don't know what that means, but this just makes your polynomials the same size. So basically you have the same orders. There's going to be some zeros. It makes everything look a lot prettier. I'll show you guys an example. This right here is how you do your, what do you call it, frequency response in terms of Z. So I'll show you guys. Let's see. And then there's another system. Here's that. And then let's see. And do I want to go too deep? Because I don't want to, I guess you guys need to know the theory a little bit before you guys go crazy. Determine the system's transfer function. Where are the poles and zeros? So I'd like everyone to try to solve this problem, or actually we'll just do it right here. It's page 2. Let's see if David remembers how to do z-transforms. So don't worry, I'm writing the same equation we have here. Y of n minus 2r cosine omega naught yn minus 1 plus r squared yn minus 2 is equal to x of n minus r cosine omega naught x of n minus 1. Okay, is that what we got? All good? So now we got to create a transfer function. So I'll tell you a hint. Everything you've learned with Laplace transform, if you're a master at that, you're already a master of the z-domain. It's all the same thing. So if I'll give you guys the cheat answer. So if you remember that y, what was it called? Y prime, correct? And then if you wanted to go the derivative of some function y of t, correct? Right? Turns into something like this. All right, remember that? Same thing with yn minus 1, okay? It's going to be the same darn thing, z of y of s, or y of z, okay? It's the same darn thing. So, and better yet, for completion, y of n turns into y of z, okay? Is that making sense? It's all the same things, and then, okay, there's an initial condition where it's like minus y of whatever 0 happens over there. So for the unilateral z transform, is that what he wants you to do? We'll figure that out later. Anyways, let's get back to your assignment. So determine the system transfer function. Let's see. Might be easier to use Euler's equation. Yeah, let's solve this. So if I wanted to solve this, let's start with the first part. So if I wanted to rewrite this equation, let me see, how do I want to show you this? Yeah, it's okay. I'm going to rewrite this. Okay, so this one's going to be 1, or let's just do this. Y of z, correct? Minus 2r cosine omega naught, and then there's going to be a z here, y of z, okay? And then plus r squared, z squared, okay? yz. All right, is that good? And then this is equal to, if I were to rewrite this again, y of z, 1 minus 2r cosine omega naught, plus r squared. Wait, z plus r2 z squared. Is that good with everybody? Same thing. You guys are going to ace this next exam, okay? It's the same material. This is where he says, shut your brain off. Just, it's the same thing. Or wake up. You're like, okay, cool. Go back to sleep, okay? That's what he's talking about, okay? Analog and digital is not that bad. The only thing you got to just remember is when you're going to digital, you're just sampling things. So stuff becomes a little more tricky to interpolate. Anyways, so that's our function right there, okay? Which is equal to, I do the following. Is anyone bothered if I just skip steps? Right, I'm gonna start with the inputs, right? This is gonna be 1, right? Minus r cosine omega naught z. Is that good with everybody? And then we gotta remember one property. Remember how, I'm literally repeating myself. Y of s, right? Remember that? Y of s and x of s, right? Now just imagine my handwriting so bad, it just starts looking like, I don't know, y is z, x is z, right? It's just y over x, output over input, okay? So here's our output, here's our input. So all we got to do is, well, we got to make sure we divide this guy under here, and then this guy just goes over there. So we get the following: 1 minus r cosine omega naught z over 1 minus 2r cosine omega naught z plus r squared z squared. There's your answer to number 1. Easy? Not that bad of a homework, right? And then let's see. And then I asked you for poles. So where are the poles in this? That's your job, okay? I'm playing. I'll do it for you guys. 3. Let's go to 4. And let's use our orange marker. I like orange. So there's one way to rewrite this. 1 minus r cosine omega naught. We can do the following, where it's going to look like this. Or let's see. 1 minus, let's see. 1 minus r, then we're going to get e to the j omega naught plus e to the minus j omega naught all over 2, right? There we go. Right? Is that good? And then we got to get through the same thing to the bottom one. 1 minus 2r cosine omega naught z plus r squared z squared, right? Is that good? We can rewrite this as 1 minus 2r e to the positive j omega, that's our positive frequency, plus e to the minus j omega naught. Okay, and those are constants, 2 z plus r squared z squared. And then someone's probably yelling at me saying, David, I can cancel some stuff. Yeah, you can cancel this, you can cancel that, makes our job easier. Now you got to start factoring stuff, okay? So let's see, how do we want to factor this guy out? Well, you can do the following. 1 minus r, that's our r, e to the, what do you call it? E to the positive j omega, right? Oh, don't forget the z, don't forget the z. Z, there we go. 1 minus z r e to the minus j omega. We got our positive frequency, negative frequency. They cancel out when we multiply them, right? And then, what do you call it? When you multiply these two together, yeah, they give you that z squared, r squared, right? And then when you add these two together, you just get this middle part. Making sense, everybody? Not that bad? So then if you wanted to, well, let's see. I do have this top part right here. How do I want to draw this? Because this is going to be a constant. How do I want to show you this? Let's see. Do I want to show you that? Yeah. I'll show you what I can do. 1 minus r. Yeah, I don't like that number. It's okay. I'm trying to think about this smartly, in a smart way. R, let's see. E plus, that's our positive frequency. This is our negative frequency. 2. And then, yeah, you just get these two poles. 1 minus z r e to the positive j omega. 1 minus z r e to the negative j omega. Okay? And then with that, because I don't like this. Because basically this right here is a constant. That's what's yelling at me in my head right now. This right here, though, if you wanted to, you can solve for this pole, where z is equal to, what do you call it? How do I want to get rid of this? It's going to be, let me see. Z is going to equal to, well, I don't want to cancel this one, because we want to get rid of this guy. Let me see. This has to equal 0. Okay. How do I make the 0? 1 minus z r e to the positive j omega. I need to force that to be 0, correct? So that means this guy goes on the other side. So if I were to do the following, z r e to the positive j omega, okay, is equal to 1, right? Z is equal to 1 over r e to the, what do you call it, minus j omega. Is that good with everybody? Everyone clear? So let me see. I feel like something's wrong here, because I don't like that. R e to the j omega. Am I doing this right? Let me see. Because I want that pole. If we plug and chug this into this, so that's R, that cancels out. That gives us our pole. Boom, we're done. Bum, bum, bum. 0.9, because I'm thinking of something different. Something's wrong right here. Yeah, I guess so. Yeah, we'll figure something out. Anyways, that's that pole, and then long story short, it's going to be plus or minus. That's what I was trying to get to you, everyone. Is that making sense with everybody? This is not making sense to me right now. Let me see. These are our poles. These are our zeros. I think something's wrong. Hold up. I think this needs to be negative. I think I'm going crazy. Let me show you guys what I'm talking about. That's what I was saying. Z transform table. Here we go. See, when you have 20,000 things to think about. Oh yeah, this is what he's going to give you on your exam, by the way. There you go. No. Where's our derivatives? No, where's our derivatives? Difference. Z differentiation. No, is that right? No. Now there's another way to see this. Time reversal? No. Where is that equation? I'm trying to find it. Let's see. No. Because basically when I have this condition, delayed unit step, that's not right. No. I'm just looking for a delay. Definition, continuity, delay. I think this is it. Let me see, hold up. Yeah. Oh, these are bad. Chegg, help me. Anyways. Because what I'm trying to say is I think this part right here that I'm trying to show you guys, see. What do you call it? This right here, I feel like this has got to be a negative. I don't know why I'm thinking that. I need to verify that table, because then this would be -2, and then this would all be negative. So then I don't have to think about anything. It becomes a lot easier. And then basically, since this is already a negative, then this becomes flipped. because this pole needs to be inside the unit circle. 1 over r, 1 over 0.9, that's not less than 1. You guys understanding what I'm saying? So let's see, if my little noggin was correct. Let's see, page 3, page 2. What I'm trying to claim is that this part should be -1. This part should be -2, right? This is -1. This is -1. -1. -2. There we go. That's making more sense to me now. Okay, that's making more sense. Okay. And this becomes -1. This becomes -1, -2. And now this becomes, okay. There we go. Yeah, now that's making more sense. This is making more sense. Okay, there we go. Okay. I'll show you guys what I was trying to do. Silly old me, you forget your fundamentals. Okay? Let's see. 1 minus, and this is what I'll try to do. R cosine omega z minus 1. There we go. Then 1 minus z r e to the positive j omega. Then 1 minus z minus 1 r e to the minus j omega, right? Where this needs to be forced. Okay, you see? R e to the plus j omega has to be equal to 0, okay? But what's another way of writing z to the minus 1? 1 over z r e to the positive j omega, right? Is equal to, does anyone bother if I do this? Right? Then just move this z over there. Is that good? And then if you want to do it for both these cases, just do minus, minus, minus. There you go. That's looking much better. And then that proves your assignment. Okay? That's what I have right here. So I just changed the frequency. You can always change it down to this. It's just a play variable. Here you have two sizes. They're different, okay? They're not the same, okay? Constants. Well, that's a variable, but they're all constant because our play variable is going to be the z, right? So did you guys like that I used no for loops in the tool? Yeah, because the whole point is I'm just trying to fill in like the matrix itself, the -10 to +10 and the imaginary and the real. I'm just trying to get that whole play field. So mesh grid is pretty good. It just punches everything. It's a function that does everything for you. And then here's my real z, right? This is the one I'm trying to actually like play with, right? And then polyval, right? Just calculates it for you. So there's another way you can do this where you can just like explicitly write this equation down. If you write this explicitly, it'll solve it for you, but you have to rewrite this all the time, and that's not good. We don't want that because I want to build stuff really quickly. So if I wanted to build another equation, I don't know if I wanted to. Actually, this is a unique resonator. You could maybe I'll show you guys with an example. Who wants an example? Let's see. Let me show you something. Because I don't think he'll show you this at all. You guys won't know this. Let's see. If I were to do the following, the unit step. Let's see. Unit step, right? And it just does this. It just goes up as t is equal to 0, correct? So if you looked at the Laplace transform for this guy, it's actually going to equal this. Let's see, is that correct? Z minus 1. Is that good? Right? So where's the pole in this guy? Actually, someone's screaming at me. Where did I get that number? Unit step, right there. Well, it's 1 over 1 minus z to the minus 1, right? Does that make sense? So okay. Let's talk about this, because I think a lot of people are gonna. This is where people are gonna mess the interview up. 1, 1 minus z minus 1. Okay. From this equation right here, right, you can tell there's a pole, right? Are there any zeros? Yeah, you can't see it. But if you convert this to the true value, this true z domain, there is a 0. So what's the z domain going to look like in this one? If I were to, maybe I should just draw my circle like this, right? That's my unit circle, right? I'm going to get a pole at 1, right? When z is equal to 1, right? And then I'm going to get a 0 right there. Is that cool? Now here's the question. If I were to draw the Fourier transform, remember how we were saying that this whole line right here, is like the Fourier transform, right? What if I just draw it? If I were to draw it like this, I'll just draw it right here. Frequency, right? How do I draw a pole on the, what do you call it, Fourier axis? I don't know, just a pole like this, right? And we said that this was DC here, right? So what's the value there? This is going to be 1. It's just a unit step. So it just does this line. So when you do the Laplace transform, what do you call it? The unit step, you're just going to get or the inverse Laplace transform of the z domain. You're going to see that it's just a line. It's not stable. Actually, I think he had a question on this. Is the unit step or the actual unit, is it stable or is it not stable? Because it doesn't do anything. It's just at DC, correct? But if it goes a little bit like a little bit negative, like it goes inside like the actual what do you call it, the circle, it's stable. But if it goes a little bit outbound, it's not stable, right? Yeah, so I think it's like called critically stable or something like that, because it's like at a point where it can break. Anyways, what I was trying to show you was this. If I were to do the following, b is equal to 1, right? And then a is equal to, let's see, 1 minus 1. Is that good? Yeah, let's see. And then this right here is going to do the following. Let's see, F9. Is that good? Come on, there we go. That's our numerator, that's our denominator, but this is our higher power, okay, z, right? And this right here is our bottom c, highest power, correct? So that, what do you call it? This equal length one, actually, what does it do? Help eq tf length. There we go. What is this function? Come on. Come on, I hate this. There we go. Equalize the length of a discrete time transfer function. Okay, so equalize transfer function length. That's what it means. Okay. Anyways, we're going to do our unit step. Anyways, run. Does that look cool? Okay, let's explain, because someone's like, well, how did you do that, David? How can I do that? As in you guys. Anyways, remember from the last assignment, you just draw your square, correct? Well, in this, I'm lazy, okay? I put square because -2 to 2, right? That's what the assignment asked. Go from -2 to 2, -2 to 2. And you know the unit circle is a square, okay? So just big circle. So be lazy like me. Or don't, I don't know. Do more work. DZ, that's the little increments. I'm just doing these little precisions. Our real axis, smaller than real. Okay, no, I'm not doing that anymore. There you go. Mesh grid, Z, polyval, and then, oh yeah, so I'll give you guys this. If you guys are really OCPD, what is it? OCPD, obsessive compulsive personality disorder. There we go. If you guys are very picky about perfection. You know how a circle is from 0 to pi, 2 pi, correct? So, okay, let's just do cosine, right? And then our sine, right? Our x-axis or y-axis, right? We're doing that. We're trying to get the components of a circle. And then the Z, this Z is just the height, okay? And I can do this as 1. So I'm drawing this circle, right? This is my actual circle right here. I'm drawing a circle, 3D circle. Plot 3, it just draws a 3D line. See that? Now let's see if I can do the following. It just changes the position. I don't know. 50. And if you wanted to do the following, boo. You guys getting your education's worth? And then you see that pole right there? Let's see if I were to grab it. It's a bad pole. Let me see. Let's tune it down. 10. Oh. See how that pole is right there if I were to zoom in? See, it's unstable. Let's see, if I wanted to pull that pole back in, then let's just do the following. R, I don't know. Is that gonna work? Yeah, sure, let's see. I don't think that worked. 0.5. Is that working? Huh, it doesn't work. No, because okay, that doesn't change anything. There we go. Because I want to change this guy. So if we know that the pole is going to move this, let's do 0.5. There we go. Now our system's stable. Is that cool? So if you did your homework and run these values, okay, now you can create your own like equations just by just running this. So everything you got that you do beyond this part, like you're setting this up, you can generalize any function based on just changing these B's and A's, okay? So any problem in your Shams outline or anything in the, Subaru book, so if you think about it, assignment 5 and assignment 6, if you tailor them perfectly, you can create the grand Laplacian Z transform tool set. So any system can be realizable. Do your, state space equations or just kick the box. You can analyze any system without using LT-Spice. Pretty cool, right? So I'm planting the seed in you guys. You guys can have fun, do whatever you want. And then let's see, what's part 2? Fourier transform. Let's see. Yeah, power, not that bad, right? If you use the freaks function, it's saying omega. Okay. What if I do this? Omega is equal to, whatever, 2 times pi. And then, does anyone bother if I do this? Times pi. And then 2 pi. Why did I put a pi in there? Or better yet, let me make it even trivial. 0 to 1 pi, right? 2 pi. Count our intervals. 0, 1 pi, 2 pi. Makes it easier for us, okay? But if I do increments of 1, right? 0, 1, 2, and then 3, and then there's that 0.14, right? So this just helps us with calculations, makes it a lot easier. Hence I did 0. Let's just keep it there. Anyways, freaks. What is our system? What did I tell you guys to do? Calculate the frequency response. Help. Freaks. There you go. Freaks. Okay. It's expecting B, A, and N. Okay, easy. B, A, omega. And then I think this needs to be figure 2. Yeah, there you go. You guys like that? And that's our DC frequency. Let me see. Let's do this. Who wants to see it blow up? There you go. Whoa, it blew up. The heck? 0, 0, 1. There we go. Oh. Does that look good? Magnitude is 100 dB or something like that. That's our first point. $50 dB. Anyways, you guys understand what's going on then? But yeah, this is just for the unit step, okay? That's what we're calculating. But anyways, if you wanted to go back to your assignment, let's do this. Do this. Boom, boom. Let's get rid of this. I'm too lazy. There you go. What's going on here? It's those poles, right? If we were to draw this line, and I think I did this for a class. Let me show you. If I were to show you something pretty cool. Let me see. Let me get this guy again, okay? Figure 3. And instead of plotting a straight line, I'm going to make this, let's see, x-axis, y-axis. Let me see. I want to do the actual B. Let me see. No, wait, hold up. There's a better way to do this. Help, freaks. Show you this. God, I hate this mouse. There you go. I want to store this number, okay? There we go. Because we want to use this number. So here's H and here's omega, okay? Okay. So let's go pull that puppy out. Oh, come on. H omega is equal to, and let's just do, I don't know, omega 2, whatever. Now let's see what happens here. And let's get rid of this here. Then, let's see, what does that do? Okay. It doesn't plot anything, okay. Plot omega 2 H omega. I don't know if that's gonna work. Oh, it did work. Okay, that's cool. I don't like that axis there. Yeah, let's see. Let's get rid of this. Plant this again. Oh, come on. 0 to 2. Okay. That's good. I'm trying to show you guys something. Let me see. Normalized frequency. So we want this again. It's Control Z. We want that. There we go. And then 20. Oh, come on. 20 times log 10 of the absolute value of omega, or H omega. There we go. Is that good? There you go. Looking better. But then I don't like this, so let's just divide this by pi. Yeah, there we go. There you go. It's looking better. Is that good? And then if you wanted to say this, x label normalized frequency. Yeah, there we go. That should be good. And is that better? Normalized frequency. And then I'll just do times pi. Oh, money sign. There we go, money sign. Okay. Money sign. interpreter LaTeX. There you go. Yay! You guys like that? Put a little pi symbol. And then, oh, let's see. Font size. That's 16. I don't think that worked. Let's get rid of that. Boom, boom. There we go. Font size. There you go. Didn't want to do that either. Font size. Too many inputs. What? Man. Never going to have fun in this class. Anyways. Is that good with everybody? Anyways, what I was trying to do was I was trying to wrap this onto this axis right here. And I think you can do that by, if I were to do the following, let me see. If I copy this, right? Call this one theta 2 or whatever. That's my circle, right? And this right here is going to be that, what do you call it? This guy right here. Copy paste. Okay. And if I were to do this cool figure right here, hold on. Yep, hold on, hold off. There you go, figure 3. Okay. So I got my mesh, correct? And I'm just going to plot the actual line. The line that is, what do you call it? Where is it? This guy right here. This is my line. No. Omega. Okay, I see what is going on. Let me just copy this again. Tweaking, y'all. I'm tweaking. Let's see. Theta is equal to omega. There you go. Now everything makes sense. And then this right here is this guy right here. Cool. Haha! We did it. What do you think? Matches 1-to-1. So what does this tell you, y'all? That this, what do you call it? Freaks, right? Is that a Fourier transform, that discrete time Fourier transform, because we're repeating. I think that's what it is. Yeah, discrete time Fourier transform. There's a discrete time Fourier transform, a discrete Fourier transform, a Fourier transform, and a, what do you call it? Fourier series. There's 4 definitions you gotta memorize. It gets very convoluted, but you guys like this? Pretty good? It's gonna help you with your homeworks? Anyways, I'll give you guys that. You guys can play with that, whatever you want to do. Anyways, let's see. Actually, better yet, if you wanted to see a cooler example, let's try this. Don't believe me? Make your own system. What do you think of that? Heck happened there? The pole is so tiny. That's our unit step, by the way. See this right here? That's what we were trying to do. Very tiny. Or let's see. If you didn't like that, let's just make it not explode. 0.9. Is that better? What the heck happened here? Whoa. Okay, anyways. Precision. Where's our precision? Yeah, that's so cool. Making sense, everybody? Everyone's gonna, and then, yeah, basically what I did was I made that unit step a little more stable, so it's inside our pole, and now we're getting a real value, 20. Cool? Yeah, 20 dB. That's something I forgot to mention. This right here is gonna be Y label power in dB. There we go. That's good. Any questions about that? Anyways, let's look at our next problem. And then, yeah, literally it's just going over that z-plane, residues. And then the reason why you need your residues is so you can kick your system, get it working. Convolution, convolving your system with the input or this input right here, get a steps response. And then same thing with, why the heck did this go crazy? Yeah, I'll edit this. The same system for this guy right here, except you're using a transfer function, the state space equation. So you just let everything run and chug, okay? So now I guess here's my final question. And yeah, is this literally looking like a copy paste of today's due assignment? Everyone's gonna turn it in. Everyone's gonna make the grader happy. Yeah, not gonna be too bad, right? It's the same answer. The first half and the second half are the same problem. It's just a different way of approaching it. Because the first half is just implementing it, and the second half is just state space. Okay? So now here's my other question, and this is what I'm trying to figure out how I want to get you guys assessed, or I think, let me see. I'll probably have to take this offline, let me think. But yeah, is everyone understanding what's going on here? All good? Any other questions? Before I end the video and then we start talking about our ABET stuff? Yeah, I'm going to keep this offline, all right? So you guys can tell me what we can design. All right? All right, have a good day, everyone.